Okay, this is the third hour of Physics 1A for May 10th, and we're going to go back to finishing up what we were talking about. So we were just talking about finding the radial acceleration of the ball at this point. We said we could do that if we found the velocity of the ball and then use this equation. So that's what we're going to do. We're going to use energy again. I'll just write the equation out again. So we have 0 equals, so we're going to have 1/2 mass times Vp squared minus its initial velocity, what's going to start from the beginning, where it was released from rest, so this is going to be minus 0 again, plus we're going to have a 1/2 mode of inertia times the angular speed at point P squared, however fast it's rolling at that point, minus its initial angular speed, which is also 0, plus mg times... So what's y final going to be now at this location? If we again say that at the bottom y is 0, so r, yep. So y final is going to be r minus, and what do I use for y initial now? We use this height, which is 2.7 r. And there's our equation. Our goal was to find Vp, but once again, we don't know what the angular speed is. But what we can do, once again, is we can just say we know that the angular speed at point P should be equal to the radius of the ball. The radius of the ball times the angular speed should be equal to v over r. So this is the relationship right here. So we can replace omega with v over r, basically. Just like we did in the last part. So if we do all of that, we can solve for Vp. Let's see, how do we want to do this? mgr minus 2.7r is going to be negative 1.7 mgr. I'll put that over here. And then we have 1/2 mvp squared plus the moment of inertia, again, is 2/5 little m times the radius squared. Omega p is the velocity at point P divided by the radius of the ball. All of that's squared, which means, again, a bunch of stuff cancels out. So all of the masses will cancel. This 1/2 cancels here with this 2 right here. So we have a 5th. And then this will almost always happen. R squared and r are going to cancel out here. So what we're left with is an algebra error right here. This should have been positive, not negative. This should have been plus. Because it's r minus 2.7r, which would be negative 1.7. We add it to this sign. All right, so we have 1.7 multiplied by r times g is equal to... We have 1/2 Vp squared plus 1/5 Vp squared. So that means that Vp squared, which is what we care about because we're finding radial acceleration, is equal to... what's the easiest way to do this? I don't know. 1/2 plus 1/5 is 0.7, so I would just do it like this. 1.7 divided by 0.7. R times G. That's what I get. .43. And then we can use that to find the radial acceleration, because it's just v squared divided by r, so it's going to be that, so it's going to be equal to about 2.4 g's. That's what the radial acceleration is. Assuming I didn't make any mistakes there. Does that make sense? I didn't square root it because I didn't see a point because it's already squared right here. So I can see how that's definitely confusing. Just, I don't know, seemed easier to just do it this way. Anyone have any questions? Yeah. Okay. So to solve this other part of it, we need to look at another problem. So we're going to look at this problem here, and we'll come back to finding the tangential acceleration of the ball at this point because this is a little trickier, a little more that goes into it. Okay. Oh, you may have a problem that's like this where it asks you to find force. Like instead of saying find the radial component of the acceleration, it might say something like radial force or the vertical and horizontal components of the force. Once you have this, you can just multiply this times mass to get the force. In this case, the only forces that would be acting on this ball would be the normal force going this way, and then its weight going this way, and then friction. I think the friction's going down in this case, but it might be going up. It's moving up, isn't it? So this is going to be something we're going to have to deal with in the next part. I think the friction's this way. I'll put a question mark there because that's something I have to think about. It's going to come up in what we do next. Right, because the friction's up, that would make it roll. No, because then it would want to roll, but it should be up. Because it's moving up, right? So the friction has to be opposite that direction. Okay, let's see what happens though. All right, so example 10. An object starts at rest and accelerates down the inclined plane as shown. We want to find the acceleration if the object is a sphere and if it's a disk. So we just, in this system right here, our goal is to find what is the acceleration. In this case, we're going to be finding the acceleration of the center of mass of this object as it rolls down this incline. And all we know is that you have an angle theta and we have a sphere and a disk, okay? This sphere could be a solid sphere or the disk could be a hollow sphere, I don't know. But what we're going to do here is we're going to say this is a solid disk and a solid sphere. So the mode of inertia for a solid sphere is the one we learned in the last problem, 2/5 mr squared. That's going to be relevant to going back and solving that. And for the solid disk, the mode of inertia is 1/2 mr squared. We'll need those for this problem. And it says mu is equal to 1.1 here. So all this really means is there is enough friction to allow the object to roll down the plane. And this is another situation where the object is rolling without slipping. Usually your problem will say rolls without slipping. This one doesn't, but this is an example sheet, so it's some of the information is missing. But this is a problem where the object's rolling without slipping. Okay, so I guess we can draw on the picture here. That's probably fine, right? Our goal is to find the acceleration of this object. And the way we're going to go about doing that is looking at its angular acceleration, because it's also going to have an angular acceleration. And we're going to relate that using torques and forces, basically, to eventually arrive at what the acceleration of the center of mass of our object is. Okay, but its acceleration of the center of mass is going to be going down the ramp like this. And I do think we're going to have to make our own picture because it's just going to get too cluttered if we try to draw on there. So here's our plane. Here's our ball. And the first thing we're going to do is just try to draw forces on this object. Try to draw one more line for the lower surface. Okay, so here's our angle theta. Okay, what are the forces that are acting on my sphere as it rolls down the ramp? And where should I draw them? So what are the forces and where do I draw them? It's just a ball. It's on a plane. What forces would act on it? Weight, normal, friction. That's right. Okay, so we're going to draw these all here with vectors. I'll use red for the vectors for the forces. So we have weight, which is going to go straight down, right? Let's just label this as m times g. There's going to be a normal force. The normal force needs to be drawn from the surface, right? Like this. So that's our normal force. In. And then the friction force should be going back this way on the surface, right? So there we go. We have friction, weight, normal. Let's also draw in this picture, as we normally do, the direction of the acceleration in a different color off to the side. So we know that the center of mass of this object is accelerating down the ramp. It's just, all this is a ball that's just rolling down the ramp. So its center is here, which is where its center of mass is, and that center is going in a straight line down the ramp. So this is going to be acceleration of the center of mass. That's going to end up being one of our coordinate directions. In addition to that, our object is also accelerating like this. It has an angular acceleration as well. Both of these are going to be constants in this case because the surface is flat. So we're going to have to calculate what both of these are, really. So we have our angular acceleration, the acceleration of the center of mass, we've got all our forces. The next thing to do is to just draw a coordinate system. So I'm going to make this the positive x direction. And perpendicular to the surface will be the positive y direction. And then we're just going to do what we've always done with these type of problems. We're going to write down our force equations. So I think we only need two of these in this problem. We're going to need a torque and an x direction equation. So let's write those down. So net force is acting in the x direction in this case. So if the x direction is the same as the direction the center of mass is moving, this is going to be equal to the mass of the object times its acceleration of the center of mass. In the x direction, we basically have two forces. There's going to be the force of friction, which goes back to the left, and then the component of the weight that points parallel to the surface. So let's draw the components for the weight in here. I guess blue or something. So one component of the weight is going to go this way, and then the other component will go this way. Okay. So this is our angle theta here. It's going to be the same as this angle here. So this side's going to be mg sine theta. Mg cos theta over here. I'm not going to write it down though. I don't think we're going to need it. So coming back to our equation though, and then in the x direction we have mg sine theta minus the friction force is equal to m ACM. All right. Now, something to keep in mind in this problem, as with all of these problems, the friction that's happening here is static friction. Because, I don't know if this is easy to understand, but as the object rolls, it basically, for a moment, the point on the very bottom is at rest, and it kind of like rolls off of the surface at that point. It's kind of similar to the way that when you're walking on the ground, your foot, when you like push off your foot, is at rest for a moment as you're walking, right? You know what I mean? With every step you take, your foot is at rest relative to the ground because you're pushing off of the ground, right? So your shoe or whatever makes contact with the ground, and while you walk forwards, whichever foot, your back foot is always going to stay still as you walk forwards, right? Did that make sense? So it's kind of similar to what's happening here when this rolls. It's like it's stepping off the surface at each of these points. Does that make any sense at all? Guess not. So it's static friction, which means that the friction force is not equal to mu times n, right? It's less than or equal to mu times n. The point is that it's not exactly equal to mu times n. We can't use this equation is what I'm trying to say. Okay. So what that means is this equation basically has two unknowns. It has the friction force as an unknown, and it has the acceleration of the center of mass as an unknown. We need to find another equation that can help us to get rid of this. So we'll stop right here with this equation, and we'll come over here, and we're going to do a torque equation. So now what we're going to do is net torque acting on our object should be equal to the moment of inertia of our object multiplied by alpha. Okay? So we're going to sum the torques about the center of mass of the object right here. So this is going to be the axis of rotation, because it's certainly rolling around that axis, right? So the weight pulls directly down, so it's not going to generate any torque. The normal force points straight up through the center, so it's not going to generate any torque. So it's really just the friction force that's actually making the torque happen. So on the left-hand side for the torque, I'm just going to write F times R. So R is going to be the radius of our object here. On the left-hand side, we just write F times R. For I here, we replace it with 2/5 mr squared, because part A is we're doing part A right now. This is still part A. Solid sphere, so 2/5 mr squared times alpha. We could go ahead and replace this now if we really want to. The next thing that we're going to do is we're going to use the other condition for rolling without slipping. These are the two conditions. Omega r has to be equal to VCM, or alpha r has to be equal to ACM. Angular acceleration times radius is equal to the acceleration of the center of mass. So we're going to make that replacement down here. We have I times alpha. Instead of alpha, we're just going to say alpha is equal to acceleration of the center of mass divided by the radius. So if we plug that in here, we're going to have ACM divided by R. And now we can simplify this equation. All of the R's are going to cancel out, and so we're going to get that the friction force is equal to 2/5 times just MACM, I think, is all that's left over. And then we can take that and plug it in up there. But before we do that, did anyone have any questions about these three steps right here? Why is the torque equal to F times R? Okay, we're doing sum of all torques around this axis. And that means we need to take the torque due to each one of our forces here, right? So the normal force goes straight through that axis, which means its lever arm is 0. mg is pulling down on the axis, so that also means its lever arm is 0. So neither one of these are going to show up in my torque equation. The only one that's going to show up is F, which is at a right angle right here, and the lever arm for F is R. So F, the force, times the distance, gives us our torque in this case. So F times R. And that's also consistent because that torque tends to rotate it around like this. Does this make sense now, what I was saying earlier, that like you can't have rolling motion unless you have this friction force here, right? If the surface was slippery, this object would not roll. It would just kind of like scoot down the ramp, basically. But as long as there's friction, enough, it has to be enough friction. And then it goes back to why this just says mu equal to 1.1. Because if it's that big, if the coefficient of friction is that big, then it's going to roll almost no matter what. It means the surface is really rough. Okay, so we have this answer for our friction force. Keep in mind that when we do this again for part B, for the disk, really only one thing is going to change, and that's this thing right here. So when we do this for part B, what we're going to get is that the friction force is equal to 1/2 MACM. Okay, so That's what we're going to get for part B. That's the only thing that's really going to change. Okay, so let's finish solving. We want to take this friction force and we want to plug it into the friction force right there in that equation to find ACM. So what we have then is mg sine theta minus f, which is 2/5 MACM, is equal to MACM. And we just need to isolate ACM. So we can cancel all the masses out. And what we're left with then is g sine theta is equal to m plus 2/5. So that should be 7/5, I think, right? Which means that the acceleration of the center of mass ends up being equal to 5/7 g sine theta, which is exactly 5/7 of what the acceleration would have been if this was just a box sliding down a ramp. So it accelerates a little bit more slowly than a box would. Of course, this box would have to slide without friction. This one's sliding with friction, and it's moving this fast. So that's the answer to part A. And if we do the same thing for part B, what we're going to get is mg sine theta minus, instead of 2/5 ACM, it's going to be minus 1/2 MACM. And then we can solve this one, and eventually what we're going to get, I think this will add a half over here, so you'll have 3/2. You'll ultimately end up getting 2/3 of g sine theta. And you can do this for any shape you want to. And you're going to get different answers, basically. And the things that roll down the ramp the fastest with the most acceleration are going to be the objects that have the smallest moment of inertia. Anyway, 5/7 is bigger than 2/3, right? So this one's faster, right? 5/7 is bigger than 2/3. Yeah, a little bit, not by much, but a little bit. Anyone have any questions? So I would like to at least introduce angular momentum today. So I might leave the figuring out the tangential acceleration part when the ball is going vertical. I might leave that to you because it is going to show up in one of your homework problems. So I'll let you figure it out, and we can talk about it after you've spent some time thinking about it, because then you're always going to get more out of something if you've actually spent some time actually thinking about it. Anyway, so there's a few different problems with rolling without slipping. You'll see some of those show up on your homework. The last thing we're going to do today is just introduce angular momentum. Oh, I forgot to mention something at the beginning of class. So for Thursday, if you want to read ahead and be kind of prepared, read F-1 in lab manual. We're going to go over this lab on Thursday. And there's kind of some activities and stuff to do at the end. It's all about error theory, error propagation, and we're going to discuss that in the second 2 hours of Thursday's class, basically. It's mostly theoretical and mostly just math, but it's kind of part of 1A, and we need to learn it before we're finished here. Okay, so for Thursday, read that. Read F1 in the lab manual, and we'll talk about it. Okay, angular momentum. All right. So let's say you take a wheel and it's rolling. So we've got maybe some kind of a bicycle wheel or something like this that is moving around in a circle, rotating with some angular speed that we call omega. And we think about what the parts of this object are doing. So let's say that I look at the very top right here, and I break off a little piece of this wheel and say, the piece of this wheel at this moment in time is moving to the right, and it has some velocity. In fact, we know exactly how big this velocity is relative to this angular speed and the radius of the wheel. If the wheel has a radius of r, then this velocity is basically equal to r times w, or sorry, r times omega, right? And if we define this direction to be the positive x direction, what's it doing? If we define this to be the positive x direction, then I would call that positive rw. Positive r times omega. I don't know why I keep saying w. If we come to the exact opposite side over here, 180 degrees away, then this object, this piece of our wheel, is going to have a velocity that's equal to negative r times omega, right? Everyone agree with that? If the velocity at the top, so this, we've got a wheel that's spinning, it has an angular speed omega, the velocity up here would be positive r omega, the velocity down here would be negative r omega, right? Would you all agree? Okay. We could also talk about momentum, right? If we talked about momentum, we would say that if I define the mass of this little piece of my object here to be m, and say that I pull an equal mass out of this piece over here, then in terms of momentum, then my momentum would basically just be mass times velocity here, right? This times its mass. You take this times its mass. And yeah, one would be positive and one would be negative. And if we summed up the momentum of the top one and the bottom one, we would get 0, right? Everybody agree with that? That if I took the momentum of this piece and the momentum of this piece, since they're going exactly equal in opposite directions, that their total momentum would be 0? And you can kind of play this game with the entire object. And what you'll find is that the basically like the net linear momentum of this object is 0 if it's just rotating around like this. If it's only rotating, then the net linear momentum is 0 for pure rotation. Right? That being said, when you have an object like this that's moving around in a circle, it still carries a type of momentum that we call angular momentum. And in order to describe what angular momentum is, what you really need to do is come up with a way of describing how this type of rotation can also have momentum associated with it. And to define how that's done, it's done in a pretty similar way to the way we define most of the other angular quantities. And let me give you like the simplest possible example first. So say I have a ball and it is rotating on the end of a string. Okay, so I've got a ball here and it's on a string that's pivoted by this point right here, and it's basically free to travel around in a circular path. Okay, and I say that at a moment in time this ball has a velocity vector, okay, that points this way. So it has a radius vector here that we call r, it has a velocity vector here that we call v, and it has an angle right here that's 90 degrees. And to add one other piece to it, it has a mass m. So what we can do is we can define a quantity that we call angular momentum, L. So L is the symbol that we use for angular momentum, L. It is a vector. And the way that we're going to define it is by taking these two vectors and then combining them together. So we have a vector here that's r, a vector here that's v, and then a scalar m. And we'd like to combine all three of these together to get a vector. The first thing we can do is we can just define what the angular momentum like magnitude will be here. It's going to be equal to the magnitude of the momentum, which is m times v, and then you just multiply by r. That's it. You just multiply by r. Just like the way that we got torque by taking r times force, you get angular momentum by taking momentum, and you multiply by the distance to the point of rotation right here, which in this case is r. But we'd like to kind of generalize this so that we don't have to only talk about simple systems like this. So another example of how this could be described is, suppose that I just take a random point in space, and I call it P, okay? And let's say next to this object, I have a mass moving along in a straight line. So I take a mass right here, M, and I tell you that it's moving with a linear velocity v. And suppose that I want to describe what its angular momentum is about this point P. So I have an object that's moving in a straight line, and I want to describe what its angular momentum about point P is. So to do that, what you do is you draw a vector from here to here. The vector goes from the point that you want to describe the angular momentum about. You define this vector to be r. I'm going to call the angle made between v and r to be phi, right here. And then say that, in general, we can define the angular momentum for this point object right here to be equal to mass multiplied by, well, I'm going to write it like this. So the momentum of my object, P, little lowercase p, is equal to mass times velocity. The angular momentum is equal to r cross p. Or in this case, basically r cross mass times velocity, which you can write, if you want to, in terms of like its size as mvr times the sine of phi. So this would be the magnitude, and this would be the more formal definition of what angular momentum is. Okay, you take r crossed with the momentum to get the angular momentum. That means that it has a direction that's going to be perpendicular to both of these vectors. Okay, I've been doing this a lot in my 1C class, so I can't remember how much of this we talked about in this class, but I know we've talked about it a little bit. What would the direction of the angular momentum vector be in this picture that I've drawn right here? So I have a mass, it moves to the right. We want to find the angular momentum about point P. What direction does this vector point? How do I figure that out? If we haven't learned enough to know the answer to this question, that's okay, but how do I do this cross product, use the right-hand rule to find the direction of L? And what direction is the point? If you all didn't know the answer to the question, it's okay. I know we've only briefly talked about like these vectors. I'm just going to cover it real quick just to remind you. Say I take a vector A like this. I take another vector B like this. Right? They have some angle between them, phi. And I ask, what's the direction of A cross B? Okay? This is how you do it. You point your fingers of your right hand in the direction of A. You rotate them from A to B. And the direction your thumb points is, in this case, into the screen. Did you all follow that? We have talked about that in this class, haven't we? So what about over here? R goes this way. Momentum goes this way. What would the direction of L be? Okay, no one's really reacting, so, and that's not the answer. So it's going to point into the page in this case. If R is this way, you point your fingers along R, you wrap your fingers to the direction of the momentum, your thumb points into the page. I think that we probably covered too much today because no one's really reacting or interacting right now. So I'm just going to go ahead and stop right now, and we'll just pick this up next time. Just to remind you, for Thursday, please read F1 in the lab manual. Okay, and we'll talk about that next time. Hope you all have a good day. I'll stick around and answer any questions that you all have. I'll try to be a little more responsive. I don't have office hours on Tuesdays. My next office hours are on Wednesday. At noon. At noon. It's Monday, Wednesday, Friday at noon. Those are the office hours. If you can't make any of those times, we can talk about finding another time to meet. Oh, we're still recording. Whoops.